Hey everybody, welcome back to section 2.8, which again we said is probably one of the most important sections of this year because it comes back in so many different ways throughout the entire chapters of the book. Okay, so can you with me really quick before we finish off what we were doing last time, can you just review with me really quick each of these shapes and what can you say? Two things about the original function g, two things about the derivative, and one about the second derivative. Remember, all these little pieces are of the original. These are all original pieces. Okay, ready? Can you do these with me? Ready? On part A. Okay, this graph is increasing. This graph is concave up. Okay, we learned that if a function is increasing, its derivative must be positive, right? And the slope of the tangent lines as I go from left to right, the slope, meaning the derivatives, are all increasing in values. And therefore, because the first derivative is increasing, the second derivative is positive. Okay, part B. All right, this function is decreasing. It is concave up. Because it is decreasing, its derivative is negative. As you look at the slope of the tangent lines, the slopes are actually increasing. And because the first derivative is increasing, that means the second derivative is positive. Okay? Now, before we go on, let me just show you, these arrows are really, really good. But let me show you one more arrow that I can add to both A and B. If you go back to A, we talked a little bit how the second derivative will really, really affect the concavity. So notice that if the second derivative is positive, the graph is concave up. And vice versa. It goes both ways. If a graph is concave up, its second derivative is positive. So I'm going to write these arrows also for part A and B. All right, let's move on. Part C. Okay, this graph is decreasing. And it looks like it's a part of a concave down. Now watch this. If it's decreasing, the derivative is negative. If it's concave down, its second derivative is negative. Because remember, up above, a positive second derivative gave you concave up. So a negative second derivative gives you concave down. Now watch this. Because the second derivative is negative, that means the first derivative is decreasing. Look at that. That's an interesting way of thinking about it with all these arrows. Because remember, if a function is decreasing, its derivative is negative. If a first derivative is decreasing, its derivative is negative. Look at all these arrows. Okay, part D. This function here is, get my colors back, there we go. This function is increasing. So watch, right away. If that's increasing, I'll do right away, the first derivative is positive. Okay, cool. I also notice that it's a part of concave downness. So therefore, because it's concave downness, the second derivative is negative. Because the second derivative is negative, I can say the first derivative is decreasing. Because the decreasing function gives you a negative derivative. Interesting way of thinking about it, right? So only if I give you two pieces of information, you can give me the whole list, right? Let's do the next page. We got everything except the bottom two, and we'll finish that off today. Okay, ready? Now this is happening at the point. What's going on at the point? Okay, at this point right now, this graph is concave up. Okay, because he's concave up, I can say right away, the second derivative is positive. Because the second derivative is positive, I can say that the first derivative is increasing. Great. Okay, so that's one answer gives me two others. I can also say that that point right there, at that point, it is a local min. It's the lowest point in that neighborhood. Because it's a local min, the derivative of a bump, the derivative of a local min is 0. So there's part A. Okay, how about part B? At that point right there, what's going on? Okay, first of all, it looks like the graph is concave down. So therefore, second derivative is negative. Therefore, the first derivative is decreasing. But also looks like I can do it this way. Watch this. I can say that at that point, it looks like the slope of the tangent line, if I drew it, the slope is flat, it's horizontal, so the derivative is equal to 0. So then I'll go this way. That means if the derivative is 0, the original function has either a local max or min, right? Some kind of bump. Well, this is a local max. In part A, we went from local min to 0, but you can also go backwards. You can say in part B that if you have a derivative equals 0, then the function above it has a bump or local max. We did part C also. And at that point right there, what's happening? This is almost kind of interesting, right? Because we're going from a concave upness to a concave downness. So that means if I was concave up, my second derivative must have been positive, and concave down, my second derivative must have been negative. So in order to pass from a positive to a negative, I must pass over 0. So at that red point right there, the second derivative is 0. We also talked about the fact that if the second derivative is 0, if I change concavity, that means my original function has a POI. So I'm changing from concave up to concave down, so therefore the red dot, the point, is a POI. It's a point of inflection. Okay. Well, what else is going on right there? At that point right there, it looks like my graph is increasing. Cool. Which means if he's increasing, the first derivative is positive. Now, here's something else that's interesting. Go back to the second derivative. Remember, if a function or a derivative equals 0, that means the one right before it, the first derivative must be the local max or min. And this one happens to be a local max. If you want to remember it, the fact that the first derivative is the first derivative is positive, combined with the fact that you have a POI, that means that point is a local max for the first derivative. Okay, part D. At that point right there, friends, what's going on? I'm going to do the POI part again. I'm going to say that I'm going from a concave down to a concave up. I'm changing concavities. This must be a POI. If that's a POI, it means the second derivative is 0. If the second derivative is 0, that means I have either a local max or a local min. Okay, I know what it is now, but if you're not quite sure, you can either, again, think about tangent lines. I'm at really positive and 0, and then really negative. Really negative. Oh, really negative slope means I must have hit my lowest. It's a local min. Another way to think about it, if you're not sure, I'm going from a concave down to a concave up. That means my second derivative is going from a negative to a positive. And think about up on part A, above on the graph. On part A, you went from a negative slope, I'm drawing a graph that has a negative slope, to a positive slope. And what did you just pass over? A local min. Another way to think about that. Okay, so we know that the second derivative is 0. You know that the first derivative has a local min. You know that the graph has a POI. And the other thing it's doing is the graph is decreasing. And because he's decreasing, the first derivative is, you got it. Okay, the last two we didn't get to last time, so let's do it right now. At these points for E and for F, what is happening? Okay, for E. Well, right now, it looks like the graph is actually kind of flat, right? So the original graph is not increasing or decreasing. Here comes a new word. It's constant. It's flat. Now, because it's flat, what do you know about the first derivative there? If you think of a tangent line at that point, do you agree that's going to be horizontal? So the first derivative, when it's constant, is 0. Okay. Well, also notice what happens. Looks like I'm a combination of concave down, and I move to a concave up. That's interesting. Okay, that means if I change from concave down to concave up, my graph must have a POI. Okay. If there's a POI, what can you say about the second derivative? The second derivative is 0. And then because the second derivative is 0, that means the first derivative must be a local max or a local min. And I'm going from concave down to concave up. All right, that means I was really positive slopes, 0, and then positive slopes. That's interesting. I wonder what this is. That means I've got very positive slopes. I'm thinking of a graph. Positive slopes, 0, and positive slopes, just like there. So what can you say about the first derivative? I'm going to put a question mark, because you think it's going to be a local max or a local min, but according to my tangent lines, I was really positive. I was 0. Okay, that makes me think maybe it's local max, but then I'm going back up to positive again. Interesting. Let's come back to that. That's an interesting question, right? Let's do part F over here. Okay, looks like at that dot, the graph is constant, which means the derivative is equal to 0. I'm changing from a concave up to a concave down, which means I've hit a POI. And if I change concavity, that means my second derivative must be 0. Which again brings about the question, is the first derivative a local min or a local max? Interesting. Let's come back to that too. Okay. So now we've seen pretty much all the different shapes that we're going to have. So can we go back to the front page and fill out everything that we need to know? Some of these we did in the last video. All right, number 1. When the first derivative is positive, that means the function must be, well, increasing. If a function is increasing, its derivative is positive. Number 2, if the derivative is negative, that means the function must have been decreasing. When a function is decreasing, its derivative is negative. Number 3, when the first derivative changes from a positive to a negative, and that was over here on this page up on the top, part B. If you notice, I went from very positive slopes, I hit 0, and I went to negative. And because of that, what did I have right in between? That means your function has a local max. Okay, and I think of that parabola, I think of that downwards parabola, I think of a graph with a very positive slope going to a very negative slope. In order to change from a positive to a negative slope, you have to pass over a bump where the derivative is equal to 0. And in fact, if you're going from positive to negative, you must be passing over a local max. Number 4 is the other way around. I'm changing from a negative slope to a positive slope, which means I must pass over, again, a bump. And what kind of bump is that? It's a local min. Great. Okay. And number 5. When the first derivative is increasing, the first derivative is increasing. Well, that was like this kind of graph. That works. Or you could also have it like this. Those were two pieces of functions where the first derivative was increasing. So I can say right away that those two pieces look like versions of concave up. And that's going to be the answer. But should we think about it a different way? Remember this. Remember all the arrows? If the first derivative is increasing, remember, if a function is increasing, what can you say about its derivative? It's positive, right? So if the first derivative is increasing, the second derivative is positive. Remember, second derivative help us with concavity. So if the second derivative is positive, remember, that means he's concave up. So two ways to think about it. You can either think about the shapes of the curves or the arrows that I like to do. Okay, if the first derivative is increasing, the function is concave up. Number 6, when the first derivative is increasing, well, it's going to be concave down because it's the opposite of number 5. But again, watch these arrows. If the first derivative is decreasing, then the second derivative is negative. If the second derivative is negative and he determines concavity, a negative second derivative means the graph is concave down. Okay, we're getting there. This one we didn't touch on last time. Let's think about it. When the first derivative has a maximum or a minimum. Okay. Well, not like this or this. That's when the original function has a max or min. But when the first derivative has a max or min. Now, if that's really tough to picture, don't worry about picturing it. Think about this. If a function has a max or a min, then its derivative should be equal to what? So therefore, if the first derivative has a max or min, or a bump, then its derivative, the second derivative, should be equal to 0, right? First derivative has a bump, second derivative is 0. Remember, second derivative is all about that concavity, right? If the second derivative is 0, what does the function have? A POI. POI, again, folks, is where the second derivative is changing from positive to negative. It's where the function is changing concavity from concave up to down, or up or down to up. And it's also where the second derivative equals 0. They all mean the same thing. Okay? So if the first derivative has a max or min, that means the second derivative is 0, which means the function itself has a POI. Okay, as we get closer and closer to undoing derivatives, we have to come up with some kind of function that represents the undoing of a derivative. Meaning, if I have f and I want to take the derivative, I get f prime. All right, that's the derivative. Cool. If I want to go backwards, though, well, that's pretty easy, right? All I got to do is undo it and sort of take away the little prime symbol. Well, that's great. But what if I give you the derivative is f? What did I take the derivative of and get small f? Well, in math, we don't know. We don't know how to write that notation. So here's what we're going to use. We're going to use a capital F for the sort of original function. If I have original function of capital F, its derivative is small f. The reason we're doing this, friends, is I'm going to start throwing graphs of derivatives at you. But I'm going to call them f. I'm going to call them small f. I'm not going to call them f prime. That's kind of too easy. AP is hard, right? So I'm going to give you the derivative graph. I'm going to call it small f. You need to talk about the original graph. Well, how are you going to write that if there's no prime on there? Well, we're going to call the original graph capital F. So if going forward is the derivative, what operations is going backwards? Well, that's the underderivative, or we call it the antiderivative. Sometimes with a dash, sometimes one word. Okay? The antiderivative is just the reverse of the derivative. It's the undoing of the derivative. And as a little peek into the future, when we get in chapter 4 and 5, it'll eventually be very, very closely related to this special word. That's the second half of calculus. The first half, you learn about the beautiful derivative and all its amazing glory. The second half of calculus, you learn about the integral, or the antiderivative, and all of its glory. Okay, so let's answer 8. We didn't even get a chance to really answer 8 yet because we had to explain it. Here's the answer to 8, friends. A function f is an antiderivative of little f if you take the derivative of f and you get small f. Okay? The capital of big F is small f. That means that capital F is the antiderivative of small f. Because if you took the derivative of big F, you would get small f. All right, look at all this great stuff. Now we get to play. Ready? All right, I'm giving you a graph. Look how it's labeled, though. You think, oh, that's the original function. No, 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 no. Remember, this is the derivative graph, and most of the times it will be the derivative. I throw the derivative at you. The AP throws the derivative at you. I need for you to talk about the original graph. What do you know about capital F? What do you know about the original graph? Okay? So what we need to do is we need to answer all these things about the original graph. Where's the original increasing based on looking at the derivative graph? Where is the original decreasing? Where does the original have a max or min? Where is the original concave up or concave down? Where does the original have a points of inflection? Okay? So as we go through each one, think about the list we made in the first page, if you need to go back and refer to it, or think about all these little lists that we made here with G, G prime, G double prime. Okay? I like the lists. I like seeing it that way, but just strict memorization is also beautiful. All right, let me reinforce these axes here so we can see better our x and y axis. Okay, so again, remember, friends, this is the derivative graph. We need to go backwards and talk about the original. And we can't really graph the original. It's hard to do. So let's just figure out what we know, knowing all the stuff we learned from section 2.8. Okay, so next to each one of these, what I'm going to do is I'm going to write what my brain is thinking. Before I even write the answer, write what this brain is thinking. And this is very good for you, friends, because on the AP, if this is a free response question, you're going to maybe have to justify how you got your answer. And the best way to justify is to write down words. And that will give you the partial credit that you need. All right, so I'm trying to find out where the original is increasing. So here in words, if the original is increasing, that means the derivative is what? If the original function is increasing, its derivative is positive, right? Okay, so on this graph, let's figure out where is the graph positive. Like literally, where is he above the x-axis, right? That's where a graph is literally positive. Okay, well, it looks like if I trace it like from here to here and from here to here, that's where my derivative is positive. Therefore, my original graph is increasing. So I'll say it's from -1 to 0 and from 0 to 1. That's where my graph is above the x-axis. That's where my graph is positive. That's where my derivative is positive. So that's where my original graph must be increasing. Now, if you want to, the AP is okay if you write it just like this and combine them. It's absolutely fine. All right, there's A. You want to try D? Try to think. The original is decreasing where the derivative is doing what? All right, in words, if the original is decreasing, that means the derivative is negative. So looking at a graph, where is the derivative? Where is this graph negative? I'd say here and here. So I would say from, let's see if this is -2 to -1, and then from 1 to 2. That's where the graph is negative. That's where, therefore, the derivative is negative. And therefore, that's where my original graph is decreasing. Okay, part C. Where does the original have a max or min? Remember, if there's a max and min on the original, that means the derivative at that point must be equal to, remember it's a bump, so the derivative is equal to 0. So you're going to look at this graph and try to figure out on this graph, where is my graph equal to 0, which is another word for the x-intercepts. So where are the x-intercepts? Here, 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 and here. Okay, if that's where the derivative is equal to 0, then therefore my original graph must have a bump, either a local max or a local min. We don't know which one yet. We could figure it out though, but not sure yet. But for now, we're just trying to figure out if it's a local max or min. Okay, so where that's at x equals -2, -1, 0, 1, or 2. Ooh, but I really do want to know if it's a local max or min. And here's how you can do it. Let's look at this bump right here. This bump is, this x-intercept, that's where the derivative is equal to 0. That's where my original graph has a local max or min. Well, let's look what happens. Right now, the derivative here is a negative value. And up here, the derivative is a positive value, right? I'm not taking the slope of this. I'm just literally looking at the x values, the y values. It's either negative below the x-axis or positive above the x-axis. Well, if I'm going, remember, if my derivative goes from a negative to a positive, remember that looked like this. A negative slopes to a positive slopes, what did I pass over? That's actually a local min. So another way to think about it, remember, if I go from a negative to a positive derivative, I must pass over a local min. So that means that this is a local min, which means this one, which is changing from a positive before to a negative afterwards, must be a local max. Now the endpoints we don't know. We don't know what's going on there because we don't know what happens. Does it just bounce backwards down or does it bounce back up? I don't know. Here, interesting. The derivative is positive and then afterwards the derivative is positive. That's back to that same question mark that we had on the bottom for E and F. We still haven't solved that, right? It's still a mystery. We'll figure it out though. All right, part D. Where is it concave up? Where is the original concave up? Remember, the original is concave up. G, we said, was concave up if the second derivative was positive That means that the second derivative is positive. That means the first derivative was increasing. Now, if you want to memorize, the original concave up means the derivative is increasing. That's fine. My brain just happens to go through these steps because I just remember it that way. But it's up to you. But the point is, you got to here. That's big. Therefore, where is the original concave up? Where my graph here, my derivative graph here, is increasing. So let's look and see. Look everywhere on this graph and try to figure out where is the graph, the derivative, increasing. That would be from like here to here, I'm increasing. From here to here, I'm increasing. And from here to here, I'm increasing. That's where the derivative is increasing, which means the second derivative is positive, which means the original graph is concave up. Cool, huh? All right, this looks like it's about negative 1.5 to negative 0.5 with, how about 0 to 0.5 with 1.5 to 2. Okay? That means, therefore, it's concave down where the second derivative is negative, which is where the first derivative is decreasing. So let's look at our graph and figure out where am I decreasing. That's the blue parts, right? Here to here, here to here, and here to here. That's where the derivative is decreasing, which means my second derivative is negative, which means my original graph is concave down. You getting the hang of it? Pretty cool though, but definitely very deep. Okay, how about negative 2 to negative 1.5? How about negative 0.5 to 0? And then finally, how about 0.5 to 1.5? All right, and the last part here, friends, is where do I have POIs? Remember, a function has a POI where the second derivative is 0, which means where the first derivative has a bump, either local max or local min. Okay, I like that line of thinking. POI, second derivative is 0, which means the first derivative, the derivative before it, or the function before it, must have a bump, or local max or min. So let's look up on the graph. Where are all my bumps? Here's a bump, here's a bump, 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 and bump. Those bumps, at those bumps, those are local maxes and mins of my derivative, which means the second derivative must be equal to 0 at these bumps, which means my original graph must be changing concavity and therefore have a point of inflection. All right, let's get those points down. How about at x equals? Notice these are points, not intervals. How about x equals negative 1.5, negative 0.5, 0, 0.5, and 1.5. Great job, folks. That's really good. That's really hard work. Again, you're looking at the derivative and you're trying to come up with answers about the original function. And again, if we call this function f, that means the original function must be called capital F, just for notation. All right, that's just about all we're going to do today. There's another graph here that would be great if you could try on your own and do the exact same reasonings. Writing words is so important and so helpful, not just for the AP as well, for the partial credit, but just to help you remember exactly what's going on. So perhaps try that one on your own, friends, and we'll check over it later. But that is basically section 2.8 in a nutshell. Really good work today, friends. I'll see you next time.